Bookkeeper 2.1, L'Hopital's rule. All right, so in the past we talked about indeterminate forms of limits. The two that we talked about was 0 over 0 and infinity over infinity. So for this lesson, for BC, we're going to add on some additional indeterminate forms. So we're going to add on 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, and infinity to the 0. Now, please understand it is your responsibility to know your indeterminate forms. Not everything is an indeterminate form. For example, infinity to the 0 is indeterminate, but 0 to the infinity is not indeterminate. All right, so again, it's your responsibility to know, just like infinity minus infinity is indeterminate, but infinity plus infinity is not indeterminate. So again, you need to know your indeterminate forms, because when you see them, you generally can rewrite your function to look something more like L'Hopital's, to where we can get the 0 over 0 or infinity over infinity. All right, so just a refresher, L'Hopital's rule we can use anytime we have 0 over 0 or infinity over infinity. And so those other indeterminate forms that we just listed on the previous screen, those other indeterminate forms can be rewritten so that they look like 0 over 0 or infinity over infinity. You can only use L'Hopital's rule, again, when it's 0 over 0 or infinity over infinity. However, you can rewrite your indeterminate forms to look like this. All right, so example 1, we have the limit as x approaches 0 of x plus tan x over sine 6x. So remember, when you guys do L'Hopital's rule, you want to take the limit of the top, see what that gives you, and then take the limit of the bottom to see what that gives you. So I'm going to take the limit of the top, so the limit as x approaches 0 of x plus tan x, which yields 0. Then I'm going to take the limit of the bottom, so the limit of x approaches 0 of sine 6x is also 0. So immediately you have L'Hopital's rule of our very basic indeterminate form of 0 over 0. So using L'Hopital's rule, I'm going to take the derivative of the top to get 1 plus secant squared x over the derivative of the bottom, which would be 6 cosine 6x. So now I'm plugging in my limit. I get 1 plus secant squared is 0 over 6 cosine 0. Remember, secant squared is 0 is 1. So I have 1 plus 1 over 6, which is 2 6, which is 1/3. All right, example 2, we have the limit as x approaches negative infinity of x squared e to the 4x. Now, when I plug in negative infinity into there, I'm going to get an indeterminate form of 0 times infinity or infinity times 0. Which tells me that I can rewrite this. Now, the easiest way to rewrite this to get a L'Hopital type situation, I'm just going to drop that e to the 4x down, making it e to the negative 4x. So I have the limit as x approaches negative infinity of x squared over e to the negative 4x. By dropping that down, when I take the limit of the top, I get infinity, and when I take the limit of the bottom, I get infinity. Now I have a L'Hopital situation because I have infinity over infinity. All right, so now using L'Hopital's rule, I'm going to take the derivative of the top over the derivative of the bottom. So I get 2x over negative 4 e to the negative 4x. I'm going to take the limit of the top. I get negative infinity. I'm going to take the limit of the bottom. I also get negative infinity, which tells me I can use L'Hopital's again. All right, so when I use L'Hopital's again, I'm taking the derivative to get 2 over 16 e to the negative 4x. When I plug in that negative infinity, I'm going to get 2 over 16 e to the negative 4 times negative infinity, which is just really 2 over infinity. Anything over infinity, remember, any number over infinity is simply 0. All right, example 3. Immediately in this example, I notice my limit is going to 1, and I know that's going to give me 2 undefined functions because I have 0 in my denominators in both of those. So I'm going to go ahead and rewrite this function by giving myself a common denominator. So I'm multiplying the left one by x minus 1 on top and bottom, and I'm multiplying the right piece by ln x on the top and the bottom. All right, so now that I have it rewritten, I'm going to take the limit of the top, which gives me 0, and then I'm going to take the limit of the bottom, which also gives me 0. So using L'Hopital's rule, since I have 0 over 0, I'm going to take the derivative of the top, which is going to give me 1 minus 1 over x, over the derivative of the bottom, which, remember, you have to use product rule, so you have x minus 1 over x plus ln x. Now, cleaning that up before I evaluate it, I'm going to see that if I clean it up, I get x minus 1 on the top, and then over x minus 1 plus x ln x on the bottom. Basically, all I did was I multiplied every single thing by x. All right, so now I'm taking the limit of the top, which gives me 0. And then I take the limit of the bottom, which also gives me 0. And so once again, I am going to use L'Hopital's rule. So taking the derivative of the top, I get 1. And then the derivative of the bottom, I get 1 plus 1 ln x. Now, if I plug in my limit as x approaches 1, I'm going to get 1 over 1 plus 0, which is 1 over 2. Example 4, we have the limit as x approaches 0 from the right of x over x. I have an indeterminate form of 0 to the 0, so I have to use L'Hopital's rule. But not only do I have to use L'Hopital's rule, I'm going to have to rewrite this using log rules to drop that exponent down. So when I rewrite this, I'm going to start by saying my original equation is simply y equals the limit as x approaches 0 from the right of x over x. And then I'm going to take the ln of both sides so that I can drop down that exponent. So I get ln y equals the limit as x approaches 0 from the right, x times ln x. All right, so now I have the indeterminate form within my limit of 0 times negative infinity, which means I can rewrite that to become a L'Hopital's problem. So I'm going to rewrite it as ln y equals the limit as x approaches 0 from the right of ln x over 1 over x. All right, so I drop that x down. All right, so now I'm taking the limit of the top, which gives me negative infinity. I'm going to take the limit of the bottom, which gives me infinity. That is indeterminate for L'Hopital, so I can use L'Hopital's rule. And so I take the derivative of the top and the bottom to get the limit as x approaches 0 from the right of 1 over x over negative 1 over x squared. I'm going to clean that up, which gives me negative x. And then I get ln y equals 0. All right. Now, since I took ln of both sides, I need to get rid of that ln on the y. So in order to get rid of the ln on y, I'm going to e both sides. So I get y equals e to the 0, or y equals 1.